In this video, we'll solve a separable differential equation involving some trigonometric expressions. Here I have sine of y times cosine squared of x times the derivative is equal to 1. Notice if I divide both sides by the cosine, because it has the x in it, I'll have an expression that's starting to separate. Sine of y times the derivative is 1 over the cosine squared of x. Cosine squared is, of course, just the secant squared, so it might be more convenient to write it that way. We can now kick the differential dx over to the other side, so I'll multiply both sides by dx, and I now have separated the variables. Next, we integrate both sides. On the right, I'll differentiate minus cosine to give me sine, so there's its antiderivative. And the derivative of tangent is secant squared, so to integrate secant squared, we just get tangent and a constant of integration. Let's multiply both sides by minus 1 to start solving for y. Cosine of y is minus tangent of x plus what I call c1, where c1 is just the opposite of c. Since c is an arbitrary number, this is just as arbitrary, so we can call it whatever we like. There we have the general solution to the differential equation. It's implicitly given because I haven't solved for y at this point. Cosine of y is appearing in the expression. But that does solve the differential equation in the sense that I have a relationship between y and x that has no derivatives in it anymore. I could try to find explicit solutions to this equation, and one way to do that would be to apply the inverse cosine function to both sides, arc cosine. Notice that when I do that, I have to apply the arc cosine to the entire right-hand side, including the constant of integration. So the c is inside the parentheses, inside the argument for the arc cosine. There is a little bit of a warning here that should be mentioned. When you use the arc cosine, it has a very explicit range. It gives you values between 0 and pi for the angles. When you apply and hit that button on your calculator and ask for the inverse cosine of a number, it's giving you the angle between 0 and pi, whose cosine is that value. In this case, what you're really assuming by taking the arc cosine is that your y, your function that you're looking for, is taking values between 0 and pi. Whether or not that's the case, you'll have to look at your application and make that decision. So be careful when you're applying inverse functions. They have specific domains and specific ranges that go with them, and you should understand that that could influence the answer of the expression. But if assuming that y is between 0 and pi, here is the explicit solution to the differential equation.